You can predict the enthalpy change of a reaction from the use of Hess's law, as we saw in the last video, or you can predict it by using heats of formation. The predicted standard enthalpy of a reaction is equal to the summation of the enthalpies of formations of the products minus the summation of the standard enthalpies of formations of the reactants. Yes, enthalpy of formation is the amount of enthalpy to form something. So you can get these values from the back of the textbook, for example. So to use this equation and use the summation, we can take account of the numbers of moles of each substance in the reactants and products by using the coefficients, these lowercase letters. So the enthalpy change of reaction is equal to the summation, parentheses, of the heats of formation of the products, where those are multiplied by the coefficients in front of them in the balanced chemical equation. And then you subtract the heats of formation of all the reactants when those are multiplied by the coefficients in the balanced chemical equation as well. There you go. You just kind of plug in values, making sure it's products minus reactants and accounting for the coefficients by multiplying those versus the heats of formation. So heat of formation is technically the standard enthalpy of formation. That is the enthalpy change to form a mole of something from the elements that it's composed of in their standard stable state. So the enthalpy change to form maybe a mole of carbon dioxide from carbon in its standard way that it normally exists at room temperature. That's coal, solid. It's graphite. And then also oxygen, the normal way it normally exists at room temperature as well, O2 gas. So there's an emphasis here on standard. So here we mean at 25 degrees Celsius and at 1 atmosphere of overall pressure. Enthalpy changes will be a little different at different temperatures, so to make things simpler, we always or generally try to deal with those at 25 degrees Celsius room temperature. So you might need to predict whether the enthalpy of formation of something is equal to 0 or if it's greater than 0 or less than 0. So let's go through a couple example problems. What is the enthalpy of formation of oxygen gas? All right, so is that positive, negative, or 0? So consider that in order to form oxygen gas, you need to get it from the way that oxygen normally exists at room temperature, that's O2 gas. So here the enthalpy of formation is 0 because there is no change in enthalpy or stability as you go from this thing to exactly the same thing. So if you're dealing with a metal like copper and it's solid, its enthalpy of formation is 0. If you're dealing with a certain gas like neon, it's typically a gas at room temperature, it's typically monoatomic, that enthalpy of formation of that is 0. But there's various diatomic elements, think Brinkelhoff, so hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. These are typically diatomic elements, so they're going to have 2 atoms of each bound to the other. You should know that the states of these, this is like a memorized thing, these are all gaseous. But bromine at room temperature is a liquid. You can see that on the periodic table, some of them. And iodine is a solid. So you should memorize that metals are all solid at room temperature except for mercury. And then the noble gases are all gases at room temperature. And then memorize these typical states of matter at room temperature for these elements. Okay, so these are all, in this way, the typical way that they exist, their heats of formation are zero, because they are the way that they normally exist. You don't need to form anything new. All right, but what if you were asked, what is the sign of the heat of formation of oxygen solid? All right, so that's negative, because in order to form oxygen solid, you would need to form it from the way that oxygen normally exists, which is gaseous. And you know that solids are more stable than gases as they have more intermolecular interactions, dipole-dipole forces, dispersion forces, et cetera, et cetera. So this is a negative change in enthalpy. So to form oxygen solid from oxygen gas is a negative change. That's a negative heat of formation of oxygen solid. What about the heat of formation of monoatomic oxygen as a gas? That's positive. If you wanted to form some oxygen gas, you would need to form monoatomic oxygen gas. You would need to form it from O2, the way that oxygen normally exists. But of course, oxygen, O2, is more stable than monoatomic oxygen because this has bonds holding these two oxygen atoms together. Whereas here we have individual oxygen atoms, no bonds. That's not very stable. That doesn't have full valence shells around each atom. So to form this, to make it less stable than the original version of oxygen, involves a positive change in enthalpy. Okay. And then what about the enthalpy formation of any combusted hydrocarbon? You want to form some carbon dioxide. You need to form it from the elements that it's derived from, some carbon in the typical way that it exists at room temperature, which is solid graphite. And from oxygen, O2, it's typically gas. All right, so you know that anytime you burn some hydrocarbon, either carbon or hydrogen or a mixture of both, anytime you react them with oxygen, that's going to release heat. That's going to be an exothermic process. That's a memorized thing. So if you're forming carbon dioxide, the product of a combustion, that's a negative change in enthalpy. You're going down in H. So that's a negative heat of formation.